In this example, we will talk about the nth roots of a complex number. Where this is going to come from is as an extension of the power rule, as when you take a root of something, for example, the square root of x, can also be written as x to a fractional power depending on what root you are doing. If you are taking the 7th root of x, you can write that as x to the 1/7, for example. That means we should be able to apply the concepts of the power rule to this, but there is going to be a caveat to this. If you consider the complex polar form of z equals modulus of z cis of theta, well, that is technically the complex polar form for this particular value. However, theta could be one number, but you could also consider any other coterminal value for that. So, if you add 2 pi of any multiple to theta, then you're going to get the same complex number, just a different polar representation of it. For example, 2 cis of pi over 4 is the exact same complex number as 2 cis of 9 pi over 4. All I have done is added 2 pi to this value, and I got the same complex number with a different polar representation. We're going to need to keep this in mind because this generation of other solutions is actually how we are going to develop all of the roots for a complex number. De Moivre's theorem would say take the complex number to the power by taking the modulus to that power and multiplying your angle measure by that power. We technically also do this to 2 pi k, but we tend not to consider it because when you're multiplying 2 pi k times a value n, a natural number n, you'll get 2 pi times nk. And this is equivalent still to 2 pi k. So this is equivalent to 2 pi k, which is why we tend to disregard it. But it's going to be very important for when we consider this for roots. When we take a root of n, we are still going to take the modulus to that same root. Instead of multiplying theta by n, we'll multiply it by 1 over n, or theta divided by n. And instead of multiplying 2 pi k as well by n, we'll multiply that by 1 over n. Or I'll write this as 2 pi over n times k. This is where our formula for the roots are going to come from. If I go back to the top of the page, we have let z not equal 0 be a complex number with polar form of mod z cis of theta. For each natural number n, the complex number z will have n distinct nth roots. For example, it would have 3 distinct third roots, or 4 distinct fourth roots, or 7 distinct seventh roots, which we'll denote with subscripts of w. And they're given by the formula mod z to the 1n power times cis of theta over n plus 2 pi over n times k. So, a little bit different than the power rule, but it's very important because we can use the different values of k to generate the solutions that we need. As discussed in the definition, we have that there are n distinct nth roots. So if you are looking for the 5th root, there should be 5 solutions. And the way that you generate those solutions is by modifying the value of k. That's what these subscripts are referring to. W sub k means that you're going to plug in a different value for k into this expression to generate your answers. If you're working with w sub 0, which is typically the first solution we list, that means we're going to take this answer and we're going to plug in 0 into k. If we are working with w sub 1, which would be the second solution, we would plug in 1 into k. If we're working with w sub 2, then we're going to plug in 2 for k. And that's how the general pattern would work. You would continue to plug in these natural numbers for k until you have developed all of the solutions you need. So, for example, if I was working with the 3 distinct third roots, I'd be plugging in 0 as my first solution, then I plug in 1 to get my second solution, then I plug in 2 to get my third solution. So that would give me my 3 answers. If I was working with the 5 distinct fifth roots, then I'd be plugging in 0, 1, 2, 3, and 4. That would give me my 5 answers. That is how we will use the root formula here in order to come up with all of the roots for a particular complex number.